Hello, my name is Rui and welcome to my presentation for Mini Project 2. In the next minutes, I will walk you through a complete pipeline that takes an underwater swim video as input and outputs a stroke prediction. What makes this project distinctive is that the entire system is built from pre-trained foundation models with no domain-specific retraining, and it runs on a consumer laptop. No GPU needed, and I will cover motivation, the pipeline stages, results, a demo, and the limitations. Let's begin. In competitive swimming, every motion contributes to drag reduction and propulsion. Today, coaches review video manually, frame by frame, slow but not scalable. The rise of foundation models opens the possibility of automating this feedback. But swim pose estimation has three persistent challenges. First, the swimmer is continuously submerged. Bubbles, splashes, and reflections occlude the body part pose, which models depend on. Second, the body orientation is horizontal, not upright. Coco-trained models have rarely seen horizontal bodies. They literally don't know which way is up. Third, in live pool settings, adjacent lane swimmers can enter the frame and confuse the detector, locking onto the wrong person. And my goal is that build something practical despite these obstacles. A pipeline that runs on a laptop requires no fine-tuning and still produces meaningful stroke recognition. Let me show you how this compares to existing work. Existing work sits on a spectrum of cost and practicality. On one end, custom-trained models like SwimmerNet achieve high accuracy, but require enormous label datasets and label-grade compute, not realistic for most settings. In the middle, work using special environments like transparent pool walls is academically clever but fundamentally not deployable in normal training pools. The closest prior work is from this very lab. They use YOLO V7 with a frame rotation augmentation for horizontal posture. They train binary classification trees. Excellent work, but they still train classifiers from scratch. My contribution is a fourth pass. Compose 3 pre-trained foundation models with 2 lightweighted custom glue layers. No retraining anywhere. The result is a system you can set up in under an hour on a personal laptop. It's not the highest absolute accuracy, but it has the best practical per effort ratio. And the heuristic glue I ate, mask-based filtering is to my knowledge, novel in this domain. Here is the full pipeline at a glance. The blue boxes are pre-trained foundation models, SAM2, YOLO V8X pose, and the BioSTM classifier. I didn't train any of them. The orange boxes are my custom processing. Frame extraction, the mask filter, the normalization with windowing. The bright orange star box, the mask filter, is a novel technical contribution, and I will dedicate slides 7 to 8. Reading the data flow, an input video is extracted into frames at 5 fps. Frames go down to parallel passes. SAM2 produces a swimmer mask on top. YOLO V8X pose detects 17 key points on row frames, not segmented ones, and I will justify that in slide 6. The SAM2 mask fades into the filter stage. The orange arrow to surprise YOLO false positives from non-target swimmers. After filtering, key points are normalized, windowed, and passed to the BioSTM, which outputs a stroke label. And to end, the pipeline runs in about 8 minutes per video. For task 1, I choose SAM2 small for 2 reasons. First, SAM2's memory attention module propagates object identity across frames. When I first tested the original SAM, it produced flickering masks and drift onto lame buoys, bright distractors. Second, the small variant runs on CPU, not GPU. The workflow is interactive but fast. I click 2 or 3 foreground points on the swimmer in the first frame, and optionally 1 or 2 negative points on lamboys. SAM2 propagates the mask to all remaining frames. If tracking drifts middle video, usually when the swimmer becomes very small, I use a review and correct loop, mark the bad frames, 8 corrective clicks, SAM2 repropagates. This converges in about 1 minute per video. Total task 1 effort for my full video, around 4 minutes of clicking. The 4 panels on the right show the resulting masks across all 4 strokes. For post estimation, I made 2 decisions. First one is that I compared the smallest variant with the largest. The large version wins by 50 to 33 percentage points per stroke, and the runtime cost is 3 seconds versus 50 seconds, which is acceptable. And the second decision, I tested raw RGB frames versus SIME segmented frames. Swimmer cut out on black background. My intuition said segmented should win, but it didn't. Raw frames won by 20 plus percentage points. My hypothesis is distribution shift. Coco models rarely see person on pure black. Their early layer filters are calibrated for natural backgrounds, and pure black disrupts the activation statistics. However, raw frames reintroduce a problem. YOLO sometimes detects non-target persons, adjacent lane swimmers, coaches, reflections. So I need the detection accuracy of raw frames and the precision of segmentation simultaneously. That tension motivates the next slide. The central technical contribution of the project. The idea is simple. For each YOLO detection, I check how many of the 8 key points fall inside the SIME2 mask for that frame. If too few are inside the detection, isn't the target swimmer, discard it. Concretely, I computed the in-mask ratio shown on the slide. Numerator, key points inside the mask. Denominator, total high confidence key points, with detection confidence above 0.3. If the ratio is less than 0.3, fewer than 30% inside, the detection is rejected. On one edge case, if SIME produces an empty mask rare, I keep the YOLO detection to avoid false rejections. The right-hand table shows real numbers. Across all 4 strokes, the filter removed 77 of 583 detections, about 30%. Look at the breast stroke. 47 detections filtered, 22%. That video had many adjacent lane swimmers. The SIME masks seeded only on the target swimmer in the first frame, correctly excludes them. I manually inspected those 47 filtered samples. They were exactly the non-targeted persons I expected. The key insight: SAM2 and YOLO has complementary failure modes. Combining them is stronger than either alone. Key point stream, time to classify. Input is 17 key points over 30 frames at 5 FPS. That's 6 seconds on full stroke cycle. Pre-processing on the left, normalized to hip center, scaled by hip shoulder distance. Interpolate missing frames from neighbors' wind size into 30 frame windows with stride 5. And during training, augment with left-right mirror flips. The architecture, a 2-layer bi-directional LSTM with hidden size 128, then attention pooling over time. Then a 2-layer MMIP producing 4 logits, about 400,000 parameters total. Training Adam W. Consing annually and gradient clipping, class weighted cross entropy early stopping with patience 15. And the critical date note, only one video per stroke, so I split each video temporarily, and I will address the implications at the end. Here are the results. Top to left, window level out of 23 test windows, the model classified 20 correctly, 87% accuracy. Backstroke and butterfly both achieved perfect 1F1. The only weak class is freestyle, with recall 0.5. Only half its window identified correctly. All 3 misclassified freestyle windows got predicted as breaststroke. Virally, they correspond to recovery phase frames where both arms extend forward in parallel, looking similar to the breaststroke glide. So the error is semantically structured, not random. And the video level, 3 out of 4 videos correct. Breaststroke at 85.7% confidence, backstroke at 67.4, freestyle at 80.4. The one error is butterfly predicted as freestyle, but it's a 5 to 5 vote tie. 0.3264 butterfly versus 0.408 for freestyle. The model isn't confidently wrong, it's confused. And the 4 hero numbers at the bottom summarize the story. 87% window accuracy, 3 of 4 video correct, and 1 error mode, and that error is a near tie. Even when the model falls, it falls predictably. Now let's see it in action. Here is the full pipeline running on the breaststroke video, the one that scored 14 of 15 windows correct. And you can see the pose skeleton overlaid in real time. The text in the corner shows the per frame prediction and aggregate confidence. And notice the prediction stays stable even when the individual frames are noisy. That's the BiSTM's temporal smoothing doing its job. Single bad detections don't flip the classification. Assignment. One pose detection is the ceiling. Butterfly has only 36% effective coverages. No classifier can recover what YOLO never extracted. The underwater dolphin kick phase is fundamentally outside the COCO training distribution. 2. Temporal split causes leakage. With one video per stroke, train and test are different time segments of the same swimmer in the same pool. The model may exploit swimmer-specific features, body shape, swim cap color, rather than genius stroke patterns. So 87% is the same swimmer recall, not generalization. 3 overfitting is visible. Training accuracy hit 1 by epoch 11. Validation oscillated 30 to 88%. 4 future directions. First, more videos per stroke to enable by video splits. Second, fine-tune YOLO on a few hundred annotated swim frames to close the butterfly gap. Third, add velocity and joint angle features. Fourth, apply temporal smoothing. To summarize, I built a pipeline composing SAM2, YOLO V8X post, and a BiLSTM with a novel mask filtering step as the main contribution. The system reaches 87% on a limited dataset and behaves predictably when it falls. The right outcome for preliminary work and strong foundation for the largest for a larger dataset. And that's all. Thank you for listening.